Lab 4, the physics of extreme sports with ropes. In this report, I will discuss the purpose of this lab, important physics principles that were used in this lab, the process in making the computational model, and the predicted data versus the observed data. Finally, I will conclude with discussion questions. The purpose of this lab is to observe the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We will find that the result of this lab is that system abides by the energy principle, as I will explain later. These are the equations that one should know when completing and analyzing this lab, including Newton's second law, Hooke's law, the momentum principle, and the energy principle. In Tracker, I chose the origin to be the attachment point of the spring, and the x-axis was horizontal while the y-axis was vertical. In order to make the computational model, there were a few variables that needed to be initialized in the code. The mass was given as 0.402 kilograms. I extracted the initial position from Tracker as negative 0.118, negative 0.629, and 0 meters. The initial velocity was 0 meters per second, and we also know that the weight force is equal to 9.8 meters per second squared. The spring constant was calculated to be 6.833 newtons per meter, with the formula K sub s equals 4 pi times m over t squared, where t is the period of oscillation, and L naught was calculated to be 0.123 meters by the formula S equals magnitude of L minus L naught. However, these values were calculated from the period of oscillation of the spring only moving in the y direction from a different video. I will explain why later. Next, I applied the formulas to the code. Kinetic energy equals 1/2 mv squared, gravitational potential energy equals mgh, the spring potential energy equals 1/2 ks squared. I ran the while loop for the total length of time observed in Tracker. Inside the loop, I used Newton's second law to update velocity and position. When you run the code, you can see that the projected motion closely resembles the observed motion of the spring in the video. The running model displays the predicted path of the motion in blue. The black arrow here represents the gravitational force, while the blue arrow represents the spring force. The graph of the energies, which is right here, shows the oscillation of the kinetic and potential energies as the system oscillates. The blue represents change in kinetic energy, the red represents change in spring potential energy, and this green represents change in gravitational potential energy, while the yellow is delta E, the sum of the three. You can see by the graph of the predicted versus observed motion, which is right here, that there's a slight difference, but they nearly follow the same paths. So for the discussion questions, for your model system, is the energy principle satisfied? The yellow line, which represents the total energy, proves the energy principle true, since it remains zero and constant. There is never a change in total energy since all energy is conserved. Using the data you obtained in Tracker, make two separate estimates of the oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. I made two separate estimates of the oscillation periods, one of the y data and one of the x data. Since the spring is constantly changing directions, the periods of oscillation are different, and you cannot use these to estimate the spring constant. Instead, we had to use the data from the video where the spring is only moving in the y direction to calculate this. In conclusion, the spring mass system abides by the energy principle and shows that energy is conserved, and the computational model closely predicts the observed. This concludes Lab 4.